Unit 3 is on functions, and in this first lesson, we are going to be determining if relations are functions. So in this first blank here, we have a relation is a set of input and output values, and it is usually represented as ordered pairs. This can be represented by an equation, a graph, a table, or a mapping diagram. And we're going to see all that below in just a few seconds here. Next two blanks are that the domain is the set of all input values or x values, and the range is the set of all output values or y values. So for example 1, we're given a set of ordered pairs. This is called a relation, and we're just going to rewrite this as a table, a graph, and a mapping. So for the table, I would take that first point 3, 1 and put 3 in the column where x is and put a 1 where the y is. And next is 2, negative 7. So we're literally just taking this point, rewriting it in our table. Next ordered pair is a negative 1, 4. So I write negative 1 for x and 4 for y, and then we have negative 2, 1. All right, for the graph, we would graph these four ordered pairs. So for 3, 1, I move right 3 up 1, and there's that first point. 2, negative 7, I go to the right 2 and down 7 from the origin. Negative 1, 4, I go left 1, up 4. And then negative 2, 1, I go left 2, up 1. So we have 2 points in the same quadrant. Just a reminder, the quadrants begin with quadrant 1 on the top right, and then quadrant 2, quadrant 3, quadrant 4. It kind of makes the letter C if you go from the first to the last quadrant. All right, finally for the domain and the range, I'm going to list all the x values for domain and all the y values for range. So let me highlight in yellow. For domain, we'll have a 3, a 2, a negative 1, and a negative 2. I'm going to start with the lowest, negative 2, and then negative 1, then 2 and 3, and just put them in increasing order. For the range, which I'll highlight in blue, we've got a 1, a negative 7, 4, and 1. So the lowest value is negative 7, and then 1, and then 4. And I don't need to repeat the 1. What'll end up happening here is when I draw my arrows, I'll just have 2 arrows pointing to 1. So the first 3, 1 goes together, which means I'm going to take the number 3 and draw an arrow pointing it to the 1. When we had the domain value of 2, the range is negative 7. So positive 2, I'll connect an arrow to negative 7. We have negative 1, 4. So from the negative 1, I'll draw an arrow to the 4. And then an input of negative 2 gives an output of positive 1. So negative 2, I draw an arrow to positive 1. And that's what a mapping would look like. So these are just showing us 4 different representations of a relation. We have a set of ordered pairs, then a table, graph, and mapping. All right, now that we know what a relation is considered a function if and only if each input value has exactly one output value. So if we look up above, the input of negative 2 only had one output. The input of negative 1 only had one output. 2 only had one output. 3 only had one output. This is an example of a function. Okay. Now what would not be an example is if we look at the problem we just did, and if one of our input values, like say this number 2, had arrows pointing to 2 different outputs. That is when we would not, the relation would not be a function. So in example 2, determine if each set of ordered pairs represents a function and explain. Kind of a shortcut or a little trick you can use, and I won't use this to explain because it's not technically the definition of a function, but look if your x values repeat at all. They're all different. If they're all different, then there's not one of them that can go to 2 different y values. Every x value has its own y, or every input has its own output, and then it is a function. So yes, this is a function, and when I give the reason, I'm going to use the definition, which is that each input value has exactly one output value. So you can say each input has exactly one output. Another option is you could have said, instead of input and output, each x has exactly one y. That would be another way to say this. All right, in part B, if we want to determine if that is a function, let's use our trick again to kind of look at just those x values and see if any of those repeat. We have a -2, 0, 1, 2, 0, 4. So it looks like 0 shows up twice here. And does it go to the same y value? Well, when x is 0 here, the y is a 3. And when x is a 0 here, the y is a 6. So does each input have exactly one output? No. This is not a function because each input does not have exactly one output. When the input is 0 or x is equal to 0, there are two different y's or two different outputs. And that is a 3 and a 6. Ooh. So, you could have just said no because each input does not have exactly one output, or no, each x does not have exactly one y. I kind of specifically for this problem showed where the problem was. With when x is 0, we have two different outputs, 3 and 6. All right, we're doing the same thing on example 3, except that now we're looking at a table instead of a set of ordered pairs. You can use the same trick. Look at all your x values. Are any of them different? No. So yes, this is a function. It asks to explain, so I'm just going to write each x has exactly one y. All right, if I look here, do any of my x values repeat? The 2 repeats. So if both points were 2, 3, 2, 3, it'd technically still be a function. So you can't just say the x repeats as your reason because it could repeat to the same y, which also repeats. But in this case, it's not the same because we have a 3 and we have a 6, just like above. So it's two different y values. So this is not a function. Once again, I'm just going to write each x does not have exactly one y. And that's because the x of 2 has two different y values of 3 and 6. All right. Example 4 is saying to look at the mapping and write the ordered pairs and then decide if it's a function. We're not asked to explain this time. I think we've done enough of that, but we'll just say yes or no. So when I look at the arrows here, I have a 2 pointing to a 3. So one of my ordered pairs is 2, 3. I'm just writing that in parentheses with a comma. Then I have a 4 pointing to a 3. Then I have a 6 pointing to an 8. And then an 8 pointing to a 5. So those are my 4 ordered pairs. Now a lot of students make this error where they think this is not a function because of the 2 arrows pointing to the 3 here. But that's okay. You can have the y values repeat every single time. What we don't want to happen is an x value going to two different y's, but two different x's can go to the same y. Okay, so this is a function because if I just look at my domain, 2 only goes to one number. The 4 only goes to one number. The 6 and the 8 only go to one number. So every domain has exactly one range. Every input has exactly one output. They can all have the same output or y value. That doesn't matter. It's the x values that we take a look at. So yes, that is a function. Where on this one it is not a function because I noticed that number 6 right away goes to -5 and 11. So when you input a number, you only want one output. But when I input a 6, I'm getting two different outputs, -5 and 11. So this is not functioning properly. Think of it like that. I always compare to like a vending machine where if you press Coke but you get Sprite, it's not functioning properly. Whatever button you press, just that one soda or whatever you're doing should come out. All right, ordered pairs here. We have a 0, 2. We have a 2, 6. We have a 6, -5. And then we also have a 6, 11. So we have x value 6 repeats twice to two different y's. meaning this is not a function. All right, last topic for this lesson is the vertical line test. This is another way to check if a relation is a function, and it works anytime you're looking at a graph. So if you look at example 5, we are given 6 graphs. The first 2 look different from the last 4 because we see distinct points. When you have distinct points, that's called discrete. And in C, D, E, and F, where it's all connected, it's called continuous. All right, either way, the vertical line test states that to be a function, so I'm going to go ahead and write function, that's only true if a vertical line never passes through more than one point. And then I'll explain that. Let me finish writing. Okay, so a relation is a function if a vertical line never passes through more than one point. Well, think about the definition. Every x has exactly one y. It can't have 2 different y's. So a vertical line, which would be representing all the same x values, should only have one y, and a line should only pass through any point or any part of the function one time. So the vertical line test, if I look at A, here's a vertical line passing through that point, that point, that point. I'm drawing a bunch of vertical segments here. Is there ever a vertical segment or line that's passing through more than one point? Nope. So yes, this is a function. It passes the vertical line test. All right, because a vertical line never touches more than once. Now on part B, you can see here that this vertical line I just drew in is touching 2 points at the same time. That fails the vertical line test, and I would say no, this is not a function. All right, now when it's continuous, you have to kind of check everywhere. So you have to imagine a vertical line through here and through here and through here and so on. And when we get to this point, notice it's passing 1, 2, 3 times through the function. Oops, sorry, through the relation. So it is not considered a function. All right, in D, if I draw a vertical line anywhere through that graph, it's only touching once, so yes, this is a function. In E, if I draw a vertical line right here, notice it's touching twice. That is not a function. And in F, anywhere I draw a vertical line, does it ever touch more than once? Nope, so it passes the vertical line test. And yes, that is a function. All right, so I know I kind of went through these quickly, but just take a look at the 3 examples, B, C, and E, that are not functions. Those do not pass the vertical line test because a vertical line touches through more than one point at a time, where A, D, and F are all graphs that do pass the vertical line test, and those are functions. This concludes our lesson on determining if a relation is a function.